Hello, this is Jonathan Gutierrez, and today I will be talking about algorithms, heuristics, and how to use them to solve problems with computers. So, first of all, let me explain what those two words mean. They're basically two different methods to solve problems. The first one, the algorithm, is a precise set of steps to achieve a reproducible result. It's something that we often do even without realizing. Basically, a lot of our daily activities, you could break them down into steps that we always do to produce a result. So, for example, the way we get to work is always the same for most people. We get on the car, then we go to this street, then we will make a turn here and there, and we always manage to get to work. So basically, just a set of steps that are well defined, that is, they can be understood by anyone, and they are reproducible. That means that if I follow the same set of steps twice, I should have the same result. And a heuristic, in contrast with the algorithm, is just an educated guess to guide your actions. So basically, let's say the first time you are going to work, maybe you are not very familiar with the place that you're going to, but you know that it's near this other landmark, or that it's near the house of one of your friends. So you start heading on that direction, and you hope that you're going to see the place that you're going to on the way. Basically, I'm making an assumption. I know that this place is near this other place, so if I head to that place that I know how to get to, I'm going to be able to get to this other place as well. And to clarify a little bit the way these two methods are different, let's see an example. Let's consider the following problem. Let's say that we're a tourist visiting a city that we don't know beforehand, and we're trying to find a museum that we are interested in visiting. So, of course, there are many different ways that we could find it, but let's look at two general approaches to solve this problem. The first one would be, let's say, maybe we already have a map of the city we're visiting, and that map includes a list of some of the most popular museums with their addresses. So we could follow a set of steps that could get us to the museum 100% guaranteed. We could first look at our list of museums, then we could find the museum that we want to visit, we could see the address, we can pin the address in a map, and then we can see our current location, and we just follow the path in the map that the map is showing us to get from our current location to the museum that we want to visit. So that's one way to solve the problem. But let's say that maybe we don't have a map, or maybe we are in a very small city, and we could say, for example, well, the city has a historical center, and I'm looking for a history museum, so it's very likely that I'm going to find it in that part of the city that I know how to get to, or that I can see indications on how to get to there all over the city. So this way, we're just basically following our intuition. We guess that this museum is going to be in the historical part of the city, and we try to see if that's the case. Maybe it's not the case, maybe it's at a different part of the city, but we're not just going at it blindly. We're following an informed guess that we're going to find a museum where we think we're going to. So these are basically two approaches, one that corresponds with algorithms and the other with heuristics. So which one would be the best way to solve the problem? And in reality, this doesn't matter, because there's a very obvious way to solve the problem. Nowadays, we all have smartphones on us, and smartphones are nothing but small computers, of course. And we know that we can pick up our smartphone and look at Google Maps. We can search the name of the museum. We don't even have to know the address, and it's going to give us a map showing us at every point or the path that we have to follow from our current location to get to the museum. So obviously, that's the most practical and easy solution. Everyone has a phone nowadays, and it's very easy to follow the instructions that the phone is going to give you. So now we have to ask, which kind of solution is this one? Is it a heuristic solution? Is it an algorithmic solution? And for that, we have to think about how computers solve problems, because that's basically what happened here. A computer solved our problem, the computer that's inside of our phones. So how does a computer solve problems? Well, computers are basically just really complex arrays of transistors and different pieces of hardware that manipulate those transistors. And these transistors are basically just circuits that are made to produce two different results for different conditions. So basically, what the computer does is just a lot of really quick and a really big number of yes or no decisions. Just this transistor has this result and passes it to the next one that has one of two results and passes it to the next one. And the way that's controlled is by what we call machine code, which is just a really big string of ones and zeros that the computer is made to understand. And you could basically write those strings of ones and zeros yourself, but that's very difficult for humans to do. So we have designed another thing, which is human readable code, which are the different programming languages and the different ways we can interface with computers. And basically we just take our brains or human thoughts and try to write some code that then is translated to machine code that is going to make the computer do what we want it to do with its binary logic. So basically the computer has to follow an algorithm for that. Every single code is basically just a way to write an algorithm, and the computer is going to follow that algorithm. It cannot come up with anything by itself. That's our job. So basically computers solve problems by translating our complex human thoughts that are heuristic and algorithmic, and it translates those complex thoughts into binary logic, which is only algorithms. There's no heuristics at this point. So basically computers are very good at algorithms. Humans are not very good at algorithms, but we're very good at heuristics and other complex types of logic. And so a lot of the time in certain disciplines such as psychology, these two methods are either presented as opposite or at the very least as a contrast between the two things. But in computer science, and especially in computation theory, which is basically the study of ways to solve problems with computers, there's something that we call heuristic algorithms. And that, if they were opposites, that would not make sense. That would be like saying dry water. But in reality, the reason why they exist is very logical and makes a lot of sense, as we are going to see with the following example. We're going to see a very famous problem in computer science that's called the traveling salesman problem. And it's very easy to describe. Basically, you have a traveling salesman that wants to go to different cities to do his business, and he starts at the city that he lives in, right? So what he's going to try to do is to get to every single city that he needs to visit. He wants to only visit each of them once, and then he wants to go back to the city where he lives. And that's really all there is to the problem. It might sound very simple, and what he's trying to do is basically just find the shortest path to do that, visit every city and go back to his city. So the reason, there are reasons why this problem has been so studied over the years, and we can see a simple example here with this graph. Every letter is basically a city, and the lines represent the distances between the city. It's very abstract, of course. We're not going to take into account the geography or anything like that, but just this, we're just going to focus on these different points, A, B, C, D, and the values between them. And so what we want to do is find the path that's going to give us the shortest value on those lines. And how would a human go about solving this problem? Basically, it's such a simple problem that a lot of people could probably just watch it and figure it out without much trouble. For example, I would say, let's say we start at city A, and what's the shortest path to another city? Well, that's the one that measures 10 going to city C, and then there's that one that measures 5 on city D, and I cannot go back to A because then I would be going to a city more than once, and so I have to take the path to B, but that one is very long and it's very likely to give me a wrong answer. So let's go back and we can look at a different alternative. I see that I can go from A to D and it only costs 15. I can still take that really short path from D to C, and then I can avoid the really long path, and I end up with the path that we can see on the screen, which is the optimal solution to this case. And what's really interesting there is that we are doing a lot of reasoning that is kind of intuitive. Like, for example, we see that that line that measures 45, we know we want to avoid that one. Or we see the one that measures 5, we know that one, we should take advantage of it. So we're following our intuition to some extent. We do some calculations, of course. We do some things that could be described as algorithms. But in reality, the thing that's guiding us more than anything else is our intuition. In contrast to this, a computer cannot really use any kind of intuition or logic or any. It has its own logic, but it cannot really take any shortcuts. It cannot say, "Oh, that line that measures 45, that's a problem." What the computer is really good at doing is saying yes or no. And a very simple way to solve this with a computer would be, okay, it's really easy to draw every single path that connects the 4 dots. So let's just draw every single path, and then let's ask the computer, is this the shortest path? And eventually it's going to find the shortest path. It's going to take into account every single possible path, and it's just going to say this one was the shortest one, which obviously a person would take a long time drawing and seeing and testing every single path. But a computer can do it in seconds. Even following a logical, intuitive process, a person is usually slower at solving something like this than a computer is. But there's a problem here. The way that the rules of the problem are really, really simple. But what if we have not 4 cities? Let's say that we have 5 or 10 cities or 100 cities. Obviously, if you were going to task a person with solving the problem, in that case, it's going to take a really long time to do it. That person might be able to do it, but it's definitely going to take a really long time. And when it comes to a computer, if the computer is going to solve it by brute force, like we just saw, by testing every single path, it's also going to take a really long time, because it can test every path really quickly, but there's such a large number as you start adding more and more cities that it's just inevitable that it's going to take a really long time, even with how fast computers are. So why is this problem difficult then? That's the reason. As you add more and more cities, the time it takes to solve the problem grows exponentially. Here, that blue line that's marked with O parentheses n to the power of 2, that line represents how the time to solve the problem grows as you start adding more and more elements. For this case, this particular problem, other problems follow different lines, but that one that's the problem with the traveling salesman problem, that as you add more elements, it takes a very, very long time to solve. And why has it been so studied? What's the motivation behind so many scientists studying and trying to solve this problem? And the reason is because if you see it in the most abstract way possible, it's basically just a problem of networks. It's finding the shortest path to connect every node in a network, and networks are all around us. The electrical grid that powers our homes, that's a network, and the roads and highways that take us to any part of the country, that's also a network. So this kind of problem just comes up naturally in a lot of different contexts, and it became a really big interest of people to find out how to solve it And then when computers started to become more popular, it became a really big interest as well for computer scientists to find how to solve it quickly with the help of a computer. And so we have this problem where it's a really difficult problem to brute force with the power of the computer. It's a really difficult problem to think a logical, intuitive solution. So what can we do? Well, it turns out that one of the first answers that were found was to use both things. So with intuition, we're able to take some shortcuts and avoid some really bad results that are obvious to us. But then when we have a lot of possibilities, it becomes really, it's going to take a long time, as we saw previously. And if we are going to brute force it, just brute force it. If there's a lot of possibilities, it's going to take a long time as well. But what if we can combine some of those shortcuts that we take by intuition with the raw power that a computer has to process data? And what comes from thinking like this is heuristic algorithms. Basically, I try to come up with a set of steps to solve a problem, and I'm going to design those steps around some intuition that I have from previous information that I know from the problem. So to explain how this works, let's look at some heuristics that are used to design algorithms. Basically, every algorithm has a certain heuristic, a certain intuition behind it that is supposed to make the job of the computer easier. So the first one and the most simple, it's called the nearest neighbor heuristic. And what it basically means is that we're going to place ourselves in one of the nodes, let's say node A, and we're just going to take the shortest path possible every single time. Let's say the first shortest path is from A to C, obviously, and so we're going to take that one. Now we are located at C. Which path is shortest now? Well, it's the one from C to D. Now I cannot go back to A, because if I do that, I'm going to be touching a single node more than one and more than two times, and that's not what I want to do. That's goes against the rules of the problem. And so the shortest path technically is the one from D to B, even though we know that it's a really long one. And the only path that remains is the one from B to A. And that's basically the algorithm. Basically, we pick a node, we take the shortest path, we go to the next node, and we take the shortest path without taking anything else into consideration. So the heuristic is, if I get as close as possible to my goal, which is taking the shortest path at every single decision, then I'm going to probably have a good result in the end. And that's not always the case. For example, when we start at A and we follow this heuristic, what happens is that we actually take the longest possible path here. But if we do the same thing starting from C, and we follow the shortest path every time that does not break the rules of the problem, we actually find the most optimal path possible. So this has the advantage that it's very simple. The rule is just take the best decision every single time without taking all of the other things into account. So it's really easy to design an algorithm with this heuristic in mind, but of course it can turn out badly, as we saw. It can give you a really unoptimal path or the worst path possible, but it's really easy to design an algorithm with this heuristic, which is why it was used at some point. But there are some better heuristics, some better forms of intuition that give us a better result. For example, there's this thing called the spanning tree, that it's a very similar concept to what we're trying to find. It's basically a path that touches every single point, every single city in our graph, and that has the shortest length possible. So it's basically something very similar to what we are trying to find. We just have to tie that last point to the beginning, and we have our cycle that goes from that touches every single city and then goes back to the origin. For example, there we can see a spanning tree for this particular graph that goes from 2 to 4, touches every single point, and we could just join 4 and 2 and we would have the result that we want. We have a path that covers every single point. And the heuristic that we're using here is that a spanning tree is really close to what we want. So if we finding a spanning tree, it turns out is very easy for computers to do. So what we can do when we want to solve the problem is just first, for a set of cities, we try to find a spanning tree, which is easy to do, and then we just join those last 2 points, and the result should be something close to what we want. So this is more abstract and more complex form of intuition, which is basically have this structure that's easy to find, and we are adding something on top of it to get what we want, and we're going to guess that this is going to give us the result, the most optimal cycle that has the shortest distance. As it turns out, that's not the case every single time, but there are a lot of algorithms that are used in many different applications, like for example for computer networks that use this kind of guess that a spanning tree gets us really close to what we want. And so there's also another heuristic that we can use that's actually one of the best that has been found in decades, where we're basically going to guess that if we have a decent solution to the problem, we should be close to the most optimal solution. Say for example, we have this graph that has points going from A to E that we're trying to join, and on the top left we can see a guess that we might have found with some of the previous algorithms we saw. We know that it's probably a decent path, it probably has a relatively short distance compared to every other option, but it might not be the most optimal. But we can guess that maybe with a couple of changes it's going to become the most optimal. Maybe we just have to move around some of the lines and it's going to give us the most optimal path. So what we do in this case is basically with that heuristic that the solutions are the optimal solution is going to be similar to a decent but not perfect solution. We're just going to take this suboptimal solution and change a couple of things around. We're going to tell the computer to do that because that's the brute force part, and we're just going to change it many different times and see if it gives us a better result. If it gives us a better result, then we can start over with this new result, trying to find a better one, and so on and so forth. So basically here our heuristic or a guess is that a decent solution is going to look a lot like the perfect solution, and we just have to change a couple of things. And while it may sound a little uncertain that it doesn't really have to be the case, it turns out that algorithms based on this heuristic are extremely precise and they are really fast. And we might, after hearing the way that these algorithms are designed, maybe it doesn't sound really too trustworthy that they're going to give us a decent solution in a reasonable amount of time. They might be able to give us a solution, but maybe not a very good one, even if they are solved very quickly by the computer. But we actually know that some of these algorithms are really precise on top of being fast. For example, here, this is a comparison between different heuristic algorithms and an algorithm that uses a different method that's much more complicated than any of the heuristic methods. That's called the Held-Karp algorithm. And we're basically comparing its solution, which we know it's very precise, to these other algorithms that are much simpler in design, but also give us a good solution. So for example, we can see that an algorithm made with the nearest neighbor heuristic here, it's about 25% off from the Held-Karp algorithm, which is very close to the solution. So this one, it's kind of imprecise, but it's really fast. As we can see there, the running time on a computer is going to be 0.28 seconds. And then at the end we have something like the Lin-Kernighan algorithm, which is the last heuristic we saw, the local search heuristic. And that one, as we can see, is really close to the Held-Karp algorithm, which is much more complicated. It's only off by 2%, and its running time is also really low. It's only 2 seconds. So This way to go about things, to use some of our intuition and mix it with the raw power of the computer, turns out to have good results in the end. And so, some closing thoughts for this presentation. Basically, what I wanted to show is that heuristic algorithms show the interesting relationship between two forms of thought, one that the computer is very good at, one that humans are very good at, and how we can combine those to produce something that is simple to understand and also very precise to solve problems that can be really, really complicated, like the traveling salesman problem. And we can also see that sometimes, for our purposes, some simple method like the heuristic algorithms provide us with can be enough. Being off 25% from the perfect solution, for example, can be in a lot of applications good enough for what we want to do. And I just think it's really interesting the way it shows us the different natures between the way we think and computers think, but how we still have to use our intuition even for those very difficult problems, and computers still are not able to do everything that we can do and need our help for some specific problems. And that's the end of my presentation. I hope you enjoyed it.